This video deals with solving problems involving the exponential model. Basically, exponential model just means something like a to the power of x. So something that's to the power of x, or it could be a to the power of maybe some minor constant, maybe say minus 0.3x. So they're kind of exponential numbers. The type of areas we're talking about are things like radioactive decay. So where you start off with an amount of material and then it has a half-life, so after so many years or whatever, it decays at half its size, and then the process continues. Population growth, similar. You have a city that has, say, 10,000 people in it, and it's going to grow, and its new population is equal to the old population. So maybe population at some initial time multiplied by maybe some number, we'd say e to the power of, say, some number k, and then t is time. So the new population is equal to the old population and then some exponential model. And it looks something like this. Here's, say, a city that starts with 10,000 people and it grows like this. So at time zero, it has 10,000 people. And over years, see these hundreds in here. Maybe if it's bacteria, they could be seconds, or they could be minutes. If it's plutonium or something, it'll be decaying. They could be thousands of years. We'll say this particular one might be days. Okay, so 100 days, this population is going to go from 10,000 people up to 20,000 people. So it sounds like a pretty fast growing place. So we're just talking about this sort of exponential growth. Or if we have exponential decay is going to look something like this one. Hang on, we'll zoom in and have a look at that. Where the exponential decay is. There's exponential decay, where something is decreasing. Its initial population is 100 here, and you can see it's getting smaller and smaller over time, whereas the population was getting bigger. It was exponential growth. And there's the exponential growth. Obviously, if we're starting something at time zero, all the numbers on this side of the axis are not really relevant. It only kicks into effect when we're at the initial number of people, 100,000 or 10,000. So that's just a picture of it. Let's have a look now at doing some of the maths. So in this question, the decay of polonium-210, which is a radioactive substance, is given by the formula M is equal to M0 e to the power of minus KT, where M0 is the mass at the start and M is the mass after T days. Okay, M is the mass after T days, and K is the decay constant, which is specific to polonium. And each of the actual radioactive materials have their own decay constants. So we'll say M is equal to 10 grams when T is equal to 0. So we know that 10, which is the mass at time 0, is equal to M0. We don't know what that is yet, by e to the power of minus K, but time is equal to 0. We're told that that's what this comes from here. So we know that the mass is equal to 10 at time 0. So find the value of M0 and K. Okay, so I'm going to have this. E to the power of minus K0 is equal to 1. So 10 is equal to M0 by 1 if you like. So that's my answer. M0 is equal to 10. Okay, the second part of the question, find the value of K. Okay, to get the value for K, which is our next task, we're going to say, let's write down our formula. M is equal to M0 e to the power of minus kt. Well, we know M0 is equal to 10, so we'll put M is equal to 10 e minus kt. Okay, so in order to work out K, we need to have something for M and K and T, and then we'll be able to work out K. So we're given this piece of information as well, that the mass is equal to 5 grams. So 5 is equal to, when T is equal to 140. So 10 E minus K by 140. Divide both sides by 10. I'm going to get 5 divided by 10 as a half. So half is equal to E to the power of minus 140 K. Get the ln of both sides, the natural log of both sides. So natural log of a half is equal to minus 140 K. And then that means that K is equal to ln of a half divided by minus 140. And that's going to give me a value of, so that's equal to 0.00495. So our formula, which they didn't ask us to write down, by the way, but our full formula is equal to the mass is equal to the initial amount, which is equal to 10, by e to the power of minus 0.00495, and then t. So to work out the mass at any particular point, I just put in the T for times, which are in days. So here's a graph of our particular polonium decaying. You can see it starts off at 10 grams of it, and after 300 days, what are we down to? We're at 2.2646 grams, okay? Okay, the next thing says, what's the mass after 70 days? Well, the mass is going to be equal to 10 e to the power of minus 0.00495 multiplied by 70. And whatever you plug that into your calculator, you're going to get what that is equal to. And that's equal to 7.07 grams. Okay, let's look at the next bit. All right, now it says, after how many days will there be 2 grams of polonium left? So in this case, I have 2. That's the many grams I will. I need to find out T. So 10 e to the power of minus 0.00495 t. So divide both sides by 10. I'm going to get 1 over 5 is equal to e to the power of minus 0.00495 t. Get the log of both sides. ln 1 over 5 is equal to minus 0.00495 t. It's important to write all this stuff out. Even when you get to know it well, don't bypass it. It's not about just getting the answers, but it is showing the steps. And that means t is equal to, I like to do these as well, that implies that ln 1/5 divided by minus 0.00495 is equal to t. So we've rearranged, we've got t on its own to find out how many days will there be 2 grams of polonium. T is equal to 325 days. 325. I think it's 0.13 or something like that. 325 days is fine. Let's go have a look at our graph actually and see if we can see where 2 grams is equal to. So here's our graph. I just rescaled it a little bit. So this is the amount of plutonium, or I think polonium, and you can see 2 grams is equal to, here it takes 320 odd days, 325 days, which is what we've got. So you can see our graph is correct as well. Hopefully that gives you some perspective how this thing works. So hopefully that helped. Thank you.